Hi, I hope you're doing well. My name is Riza, and I'm very grateful for this opportunity to share with you what's the topic that I'm learning about in this class, and that's very related to my project. And it's basically why machine learning on the real world constraints and has a lot of issues and it fails in the real world, even though it might have a great results in the lab. One of the reasons I became quite interested in this topic was understanding how AI very a key point in a real world military and defense system, and companies like Palantir are on top of that. um, and I got even more interested since I'm from Iran, um, and there's a war between Iran and US, and became even more interested to see how all this uh, technology world is going around. So one thing is a high accuracy model is not automatically a deployable model. So basically, it's not just the whole story just saying, oh, it has a really high accuracy. Basically, there are a lot of issues a model can face in the real world, and that can be a latency, noisy data, a missing data, hardware limits, network failures, and a lot of bunch of different other reasons that they exist in the physical world, but in the lab and the theory, it has no issue. And to in terms of that, um, it reminds me of my taking my own classes related to machine learning class, and all I was looking for was just getting a high accuracy model. And now I know that that's not enough. More important than that is how is it responsive in the real world. Um, so what would be the changes after deployment that makes a model might like fail in the real world? And I think these are the certain items, the basic items that can be changed. One of them is latency. Prediction arrives too late, and timing matters, and that's also very important for military or even for defense system for self-driving cars. It's very important. The noise is the sensor input data is corrupted. So if the sensor is not right, it's not capturing the right information. That can be another issue. Packet loss when the data never arrives, that's also a big issue. If you have no data, the model is not going to do anything. Staleness is basically data if it's old by the time it's used. Certain models in the real world requires updating data in seconds, and using the old data can be a lot problematic, and it can actually affect the accuracy by a lot. Another thing is compute limits. Edge devices has less power and memory, and that's true because you need to have a lot of memory and power in certain models to run. If it's specifically if it's new and it uses a lot of bigger data, that small computers might not be able to handle that. And a model can be cracked, but it still fail, right? So raw accuracy is what I just told you, that like on a machine learning class, I was trying to get that number, be able to get the highest accuracy on my model, and I thought that only that thing would be enough for me to thinking that my model was going to be perfect. But the truth is, effective accuracy says is that correct, and if it's on time, time is matters on that. A good example, accuracy can be 92%, but effective accuracy is 0% and 200 milliseconds delay, and that can be for self-driving, for any other machine learning model that can be run in the physical world that we need a lot of accurate data on it. Best lab model is not the best deployment model. Complex model has a higher clean accuracy, maybe less stable, and simpler model has lower clean accuracy, maybe more reliable under stress. And where this matters, there's a lot of real world examples that we can use for um, when it comes to this matter. And so a lot of self-driving cars, they have Teslas, they have that, and if they if they're if the only the model was good, but if it could have been it could have been failed in the real world problem. And other examples of hospital and factory machine and IoT devices and other a lot of bunch of different examples as well.